the fact that the room is really full today says that we're really in kind of a different era in awareness of the issue of climate change. What's really brought it home to me is that I get more questions now about climate change anxiety than about climate change solutions. But what I want to do is present what I would call a guardedly optimistic approach. I want to explain how, especially based on work we're doing here, but around the world, there is a path forward, and it's a path forward that allows us to build a combination of robust economies and vibrant communities. I'll spend just a couple minutes characterizing where we are with climate change, where we might be headed, and then I want to unravel kind of piece by piece how we can build a durable set of solutions. I think everybody's aware of the fact that the climate has been warming over more than a century. Essentially, no question that we have seen dramatic warming on the land and on the oceans. A few years ago, when the Intergovernmental Panel on Climate Change, the official body that reports on where we are with the science, said that there's no question it's warmed, it's unequivocal, and it's extremely likely, more than 98% likely, that the majority of the warming over the last half century or so is caused by humans. Rather than provide you with a lot of details of why we have this level of confidence, I want to take you back a few more decades. This is a paper that was published in April of 1896 by a brilliant Swedish chemist, a gentleman named Svante Arrhenius. And it's about what you would expect to happen in terms of climate if you were to double the concentration of carbon dioxide, the main greenhouse gas, in the atmosphere. And what's striking is that in 1896, 123 years ago, Arrhenius knew the three key things that you need to know to make an accurate assessment of the effects of CO2 on climate. He knew that carbon dioxide is a heat-absorbing gas. He knew roughly what wavelengths it absorbs, and absorbs the energy that you and I emit, or that objects that are about our temperature emit. He understood that a warmer atmosphere holds more water vapor, and that water vapor is a powerful greenhouse gas, amplifying whatever the effects of carbon dioxide are. And he understood in 1896 that over many decades there's a gradual partitioning of carbon dioxide between the atmosphere and the oceans, with most of it eventually ending up in the oceans. You take these three pieces and you put them together, you can come up with an estimate of what happens if you double carbon dioxide. Arrhenius got about the right answer. And for the last 123 years, there have been literally tens of thousands of scientific papers that have challenged each one of those three fundamental pieces of our understanding and not found any of them to be incorrect in any way. So all of our research about fine-tuning has been about, are there factors that amplify a little bit or suppress a little bit the amount of warming? What happens in terms of the spatial distributions of temperature and precipitation? And what happens to the temporal distributions and the rate at which these changes unfold? I think the fact that this understanding has been robust for more than a century provides a little bit of a grounding about why we feel like the challenge is well understood enough to take action on. The way I think about it is that the fundamentals of climate change are understood kind of at the same level as which we understand the function of an electric motor or a fluorescent light. What we also know is that we have clearly exited the era where climate change impacts are about future hypotheticals. We're seeing climate change impacts around the world now, and we're seeing impacts that are increasingly severe, widespread, and in some cases irreversible. I'm going to highlight just a few of the kinds of things we're seeing, and these are well known to most of you, and they're in the news almost every day. It's a picture of the Oroville Reservoir during California's historic drought from 2012 to 2016. This is the same reservoir that had the spillway damaged by too much precipitation in 2017. And what we know with a very high level of confidence is that this kind of pervasive drought gets to be more and more frequent as the summertime temperatures get to be warmer. essentially no question. It's a picture of the Lake Fire from 2016. 4 of the 20 biggest fires that California has ever experienced have been in the last 2 years, and there's no question that there's a strong link between warm summer conditions, dry fuels, and the propensity for fires to reach these catastrophic magnitudes that we've seen. There are other factors that are involved in the increase in wildfire as well, but there's no question of a role for climate change. The third example I want to talk just briefly about is this super heavy precipitation we're seeing with recent hurricanes. This one's from Hurricane Harvey near Houston. And we know, have known for a long time, that a warmer atmosphere holds more moisture. We know that a warmer ocean can allow hurricanes to persist for longer amounts of time. And we know that a decrease in the temperature gradient between the equators and the poles tends to slow the steering winds so that hurricanes now have a potential to stay around for days rather than hours. And all of those contribute to the historic precipitation that we're seeing in places like Houston. So that there's no question that there's a link with climate change to the kind of events that we're seeing that are really causing significant disruption. In the last days, you've probably read about the more than $30 billion of liability that PG&E faces for recent wildfires in California. If we look into the future, the simplest thing we can say is that the more it warms, the more we risk impacts that are truly unmanageable. And I want to talk about thinking about these risks in a slightly different way than you've probably heard about. And that's that we have a tremendous ability to adapt to changing circumstances. Humans are amazingly adaptable species. And as long as things aren't fundamentally out of control, we can adapt. But there's a risk with large amounts of warming that we pass a series of tipping points that change the world from one that's manageable fundamentally to one that's fundamentally not. And I want to talk about this a little bit, setting the stage with a picture of 2 possible futures. If you look at the top figure, the blue banner across the bottom is essentially what we might expect in a world of ambitious mitigation. This is a world that stabilizes global temperatures at somewhere between 1.5 and 2 degrees Celsius above pre-industrial levels. It's a world where we see about as much warming in the future as we've seen from the start of the Industrial Revolution till now. The amount of warming is shown on the left-hand panel here. And it's a world where, I'll argue as we go along, we can fundamentally use the adaptation tools that are available to us to manage the impacts of a changing climate. In the pink banner across the top figure is a world of continued high emissions. This is a world that has not only warmed something like 8 Fahrenheit since pre-industrial, but it's a world that's warming at almost 1 degree Fahrenheit per decade. And I'd argue, and it's a world that's shown here in the right-hand image at the end of the 21st century. This is a world where most continental areas are 8 to 10 Fahrenheit average warmer than they were in pre-industrial times, and where there are a wide range of lines of evidence that indicate that we really can't even predict what the impacts would be. The probability of cascades and tipping points is so great that we're really on very thin ice when we try to predict specifics. I also want to talk about 2 important aspects of the evolution of these impacts over time. If you look at the period from now until pretty close to mid-century, the striking thing about the 2 temperature, call them banners maybe, for what happens is that there's really a lot of overlap between what happens in a world of ambitious mitigation, the blue banner, and a world of continued high emissions. They don't really separate over the next few decades. And you can think about this as an era of committed climate change. This is an area of, think about it as climate responsibility. A bunch more changes are going to occur. We need to be prepared for those, and we need to make investments in dealing with them. The second half of the century is really an era of climate options, where decisions that we make one that we should have made a decade or so ago and that we'll make for the next decade will really control whether or not those two banners do separate or not. And they control the difference between a world that's fundamentally manageable and one that's not. Let me talk just a little bit about what kind of tipping points we might anticipate. And with each of these, we have a very high level of confidence that there is a tipping point. We have a low level of confidence about where it is. We have high confidence that we haven't passed it yet, and we have pretty high confidence that in that world of continued high emissions at the end of the century, a world that's maybe 8 to 10 degrees Fahrenheit above pre-industrial, we will have crossed one or more. One of the most important ones concerns sea level rise. This picture of an ice sheet in Antarctica. And there's an incredibly important geophysical factor that creates a tipping point that commits us over some centuries to many meters of sea level rise. The nature of this tipping point is because ice is really, really heavy, it pushes continental areas down. And if you look at the surface of the rocks under Antarctica, they're sloped inward from the coast. And once the grounding line, where the edge of the ice is sitting on the rocks and no longer floating, passes this point where the continent is tipping downward, going inward, the ice becomes fundamentally unstable. Even if we cool the climate again, it will continue to retreat as a result of the physics of the way ice moves. So there is some point at which large parts of Antarctica cross a tipping point such that even if we cool later, we'll see over a few hundred years several meters of sea level rise. During the 21st century, in the world of ambitious mitigation, we might see another 1 to 2 feet of sea level rise. That's going to cause real problems. It's already causing real problems. During the 21st century, in the world of continued high emissions, we might see 3 to 4 feet of sea level rise, and the most recent estimates from NOAA are numbers up to 9 feet of sea level rise. But once we pass this tipping point, we're committed over the next, say, 400 years to something like 50 feet of sea level rise. Now, 50 feet of sea level rise totally eliminates most coastal cities. Dozens of small island nations fundamentally disappear. And to the extent that there's a truly existential component to climate change risk, this large amounts of sea level rise from ice sheet collapse really represents a fundamental one. I mean, and it's interesting and important to recognize that that's changes over several centuries, but if you think about the world's great coastal cities, almost all of them have been there for several centuries. A second tipping point I want to talk about operates in a fundamentally different way. This is a tipping point such that even if we reduce human-caused greenhouse gas emissions to zero, emissions continue from the non-human parts of the world. This is a picture of a frozen soil in eastern Siberia. It's called a Yedema soil, and it contains very large amounts of organic matter that are frozen into it. It's organic matter that's accumulated over the last 50,000 years and represents an amount of carbon dioxide equivalent that's about 4 times the amount that's in the atmosphere now. Most of you know that the high latitudes are the part of the planet that's warming most rapidly. As these frozen soils thaw, this organic matter, it's basically frozen grasses and little plants, is exposed to the atmosphere, and we know from experimental studies where people chopped it up and thawed it out that this can decompose rapidly. Some of it decomposes as carbon dioxide, some of it decomposes as methane, an even more powerful greenhouse gas. And as it does that, we risk crossing a tipping point where continued thawing of the permafrost results in an increment of warming that is sufficient to cause the next amount of permafrost to thaw and gets us into a vicious cycle. And once we pass that, even if human emissions of greenhouse gases are brought down to zero, we'll see a continuous increase in greenhouse gas concentrations and a continuous warming. So this is a tipping point where the warming becomes potentially unstoppable. The third kind of tipping point I want to talk about is more of a social one. And climate change is a complicated problem. We need the world to work together to solve it. And there's genuine concern that the ability of the world to maintain things like cohesive governments really depends on the amount of warming that occurs. This really beautiful work from my colleague in the Department of Earth System Science, Marshall Burke. And what Marshall and his colleagues observed is that when you look at most climate change impacts that we have been able to explore in detail, they have the structure that you can see here, that temperature has relatively little effect, and then you kind of fall off a cliff. This is the pattern for corn yield. But you see the same thing if you look at, for example, worker productivity. And the temperature doesn't make much difference. You hit some temperature, fall off a cliff. If you look at whole economies, you see a similar thing if you look back in time. For countries that are in places that are currently cool, an unusually warm year results in an increase in GDP per capita. In countries that are currently warm, an unusually warm year results in a decrease in output per capita, reflecting this kind of pattern expressed over the hundreds of thousands of components that go into making a macroeconomic GDP. So if you take this pattern, observed from the data of what's happened over the world's economies over the last 50 years and say, okay, let's take that sensitivity and now we'll put it into these projections of what a world of continued high emissions might look like at the end of the century, you get a pattern like this one where the countries that are shown in blue benefit. They get an increase in per capita GDP from the warming that occurs, and the countries that are shown in red have a deficit, a decrease in per capita GDP from the warming that occurs, and the effect is large. You can see that the impact in Europe is that projected warming would increase per capita GDP by about 50%, and the projected warming at this level would decrease per capita GDP in Southeast Asia and Sub-Saharan Africa by about 75%. Of course, there are many, many other factors that influence per capita GDP on top of this, but this temperature sensitivity emerges very clearly from the observations to date. And when I look at a pattern like this with essentially all of the developing world suffering profound negatives from a changing climate, and much of the developed world experiencing positives, it speaks to me about the risk of a world that becomes ungovernable in terms of approaching solutions that need to be addressed by the world community taken together. So there are at least these three kinds of tipping points that we need to be aware of. One related to commitment to large amounts of sea level rise. A second one that's related to the possibility that the warming becomes a vicious cycle that can't be stopped even if emissions go to zero. And the third one is a little less well established, but it speaks to the risk that if climate change is producing divergent effects in different parts of the world, there's a real risk that we wouldn't have the ability to produce the kind of governance that's necessary to yield real solutions. So how much time do we have to solve the problem? A really useful way to think about this, I have a point here. The way to think about this is that there's a strikingly one-to-one relationship between the amount of greenhouse gases that are emitted by human activity from the start of the Industrial Revolution till the time the last ton is emitted, and the amount of warming that occurs. And so we know with a high level of confidence that if we want to have a 66% chance of keeping the total warming below 1.5 centigrade, which is the level that's been discussed most recently in the Paris Climate Agreement, we can release 2,790 billion tons of CO2. And it sounds like a really, really big number. And you say, well, great, why worry about it? But the number that we've already released through 2017 is 2,220 billion tons. That means that in some sense, the remaining budget is a 570. It's a small fraction of what the lifetime budget was. And the rate at which we're emitting, in the 2017 is the most recent year for which we have data, was about 42 billion tons per year. So, you guys are Stanford graduates, you're good at arithmetic. You divide 41.7 into 570, and that says that we're essentially committed to a warming of 1.5 Celsius if emissions continue at the 2017 rates in something like August of 2031. Put that in your calendars. Now, the reason that I'm optimistic isn't because I think we can maintain the budget within this level, but I think that the important difference we want to focus on going forward is finding ways to decrease the emissions and keep us in a world of ambitious mitigation in contrast to the world of continuing high emissions. And at least for me, it's about finding the accelerator pedal. And that's what I really want to talk about for the rest of this time. So how are we going to solve this problem? There are 5 key pieces, and unfortunately we often only talk about the technology piece. Technology piece is important, but it's far from the most important. The 5 pieces are technology, finance, somehow we got to pay for this, policy, how do we incentivize the right behaviors, adaptation, how do we deal with the climate changes that can't be avoided, and leadership. So before I start talking about the specifics, let me say just one more quick thing about the nature of the problem. You know, everybody has their favorite thing that's producing greenhouse gases, and for some people it's transportation, and for other people it's electricity. Some people care about building heating and cooling. But a lot of the reason this is a hard problem is because there are greenhouse gas emissions associated with almost everything in the economy. There certainly is some that comes from transport, although if you look at the global total, transport's only about 15%. Electricity is a big sector. Making things, heating and cooling buildings is a big sector. A really important sector that we often don't focus sufficiently on is the one at the top that's shown in green, and is agriculture, forestry, and other land use. In many senses, this ag sector is the biggest contributor to greenhouse gases, and it's one of the ones that's the most challenging. The ones that we're really set to make rapid progress on are mostly the electricity and transport sectors. Here's another way to look at that same set of data. You know, we tend to talk all the time about carbon dioxide, which is the top bar there. We're currently getting just a little more than 2 watts per meter squared out of carbon dioxide. And 2 watts per meter squared doesn't sound like much. That's like one little Christmas tree bulb. But there are a lot of meters squared in the world, and if you add enough of them, you get a profound impact of warming. But it's not the only greenhouse gas. That second bar, it says other WMGHGs, other well-mixed greenhouse gases, has got methane, natural gas, which comes not only from oil and gas production, but also from agriculture and animal husbandry. Nitrous oxide, laughing gas, is an important climate change agent that comes mainly from agriculture. It comes from the management of manure and from putting too much fertilizer on fields. And halocarbons, refrigerants that are, and another one of these sort of sticking points in climate is we deploy more and more air conditioning to help people adapt to rising temperatures. We use more and more of these refrigerants that are powerful greenhouse gases. It's also important to note that there are some human-made gases that are making it cooler, and that includes the 2 blue bars at the bottom, which are labeled as aerosols, is basically the kinds of pollutants that come from burning diesel and from coal-fired power plants. And the particles, profound impacts on human health, but they are making the climate a little bit cooler. And as we have made progress in cleaning up air pollution, we actually have amplified the amount of warming we get from any given mix of greenhouse gases. Okay, now I'm ready to transition to the solutions portfolio. And I want to emphasize that there's no single solution that is a total home run. I like to say there's no silver bullet, but there is silver buckshot. And it's everything from increasing efficiency to being thoughtful about adaptation. And let's start looking at what we can do to get the carbon out of the energy system. The first thing we can do, and by far the most cost-effective, is to increase efficiency. This is a picture of Jim Sweeney. I don't know if anybody took a class from Jim Sweeney in MS&E, but has been California's champion of energy efficiency for a half century, and he's just demonstrated with convincing detail that it's the cheapest, highest impact thing we can do to decrease the emission of greenhouse gases. The second thing we need to work on when we look at managing demand is the growth of human population. There have been a number of studies now that have shown that simply meeting existing demand for family planning can reduce emissions with an abatement cost, a cost per emissions reduced, of about $1 per ton of CO2. And across the rest of the economy, we look at costs from anywhere from $10 to $1,000 a ton of CO2. So managing demand across the full spectrum of ways that we can do it, super important. Often these are the most cost-effective. In fact, they yield economic benefits. The second thing we need to do is focus on making electricity carbon-free. I don't know, does anybody recognize this particular PV array? This is Stanford's first large-scale PV array. It's in Kern County. It's a 50-megawatt array. And when Stanford's second big PV array comes online, which will probably be in next year in Fresno County, the university will be producing more electricity from photovoltaics than it consumes on an annual basis. The next thing we need to, one thing, backwards. The other thing that's really striking about 100% non-emitting electricity is that we have now passed a threshold where over almost all the world, electricity from renewables, especially wind and solar, is cheaper than electricity from fossil fuel. For the next generation of PV array that Stanford has bought, the long-term purchase price for the electricity is 2 cents a kilowatt hour, and that's about half of what you would need to pay for just the fuel to make electricity from natural gas or from coal. So Stanford's approach is not only making it consumer of 100% renewable electricity, but it's also saving the university money. And the most recent studies indicate that over 2/3 of the world, renewables are the cheapest way to add electricity. There's some reasons that we're not seeing it go instantly everywhere, but cost isn't the main factor that's limiting at this point. So once we've got 100% renewable electricity, we need to electrify as much as possible. And that includes things like electrifying light transportation. And we've reached a transition, I would argue, where in many environments, the electric vehicles are not only the lowest polluting option, but also the most attractive in terms of the owner's experience. I don't have a Tesla. I wish I did, but the electric I have is really fun to drive, and it's just an outstanding car. And then there are some things where we truly don't have technology alternatives. That includes things like making cement or making steel or flying airplanes. And for those, we need to use carbon offsets so that the emissions from the manufacturing or flying are offset by the removal of CO2 into either something like growing forests or are captured from the atmosphere and pumped underground. The photo on the right-hand side is a picture of an ethanol producing plant that's in Decatur, Illinois, and it is currently in the ethanol manufacturing process capturing and pumping underground 1 million tons per year of CO2. It sounds like a lot, and it is a lot, but it's a tiny fraction of what we need to do, but it's a wonderful technology demonstration. So when we look at the energy options, the striking thing is how many there are and how cost effective they are. And they go from wind and solar to biomass electricity to net power, the the electricity generation system with built-in carbon capture and storage that's currently deployed in Houston, to large-scale hydro, to nuclear. And we can talk about nuclear later if you want. There are some big challenges, and the biggest challenge in transitioning to 100% wind and solar powered electricity system is how you do the storage. It's not that hard to figure out how you do storage for a few minutes or a few hours. Sources like the batteries in the Tesla Powerwall work really well for that. Once you get the longer term storage, it really gets to be a lot more challenging, and we don't have all the pieces of the technology answer. One key piece is going to be like what you see in the upper right-hand photo. That's a picture of Stanford's central energy system. I don't know if you guys have visited. I think it's the coolest part of campus. And it basically is 3 gigantic tanks that store hot and cold water. And the basic idea is when we have renewable electricity available, we use that electricity to make hot water and cold water that we can use to heat and cool the buildings. And then when the sun's not shining, the wind's not blowing, we still have that hot and cold water that's available. Now, those of you who are keeping up with Stanford news probably noticed that there were a couple of cooling curtailments this summer that indicate we still have a couple of kinks that haven't been worked out entirely, but it has the potential to be just an incredibly important energy storage system. And I talked about when we talk about the cost of energy storage, it's about $100 a kilowatt hour for the batteries and probably about $10 a kilowatt hour for the thermal storage. And another set of options that's probably more like $1 a kilowatt hour is pumped hydro. This is a nice example of a purpose-built reservoir where when the sun's not shining, the water runs from the top reservoir to the bottom one. When the sun is shining and you got tons of extra electricity, you pump the water from the bottom one to the top one. And you can think about this as just a giant battery, but it's a giant low-tech battery that's made of dirt rather than cobalt and all these things that are hard to mine. And then a final set of storage technologies that I think will be attractive in the long run is we're getting better and better at making chemicals from electricity. And when you were in junior high, you probably did experiments where you use a battery to electrolyze water into hydrogen and oxygen. If you have a lot of free electricity, you can make hydrogen from it. And once you have hydrogen, that can be a raw material for making a wide variety of useful chemicals, up to and including, if you wanted to, jet fuel or other hydrocarbons. So I think in the long run, this pathway is going to be incredibly important for producing large amounts of storage that mean we can have the kind of grid reliability that hopefully gets us away from the PG&E power cutoffs. Also, we're seeing technology advances that are extremely important in a wide range of other areas. It's a picture of the Impossible Burger, and I mentioned that the largest source of emissions overall, the largest source of climate change forcing is from agriculture, forestry, and other land use. The meat production is probably the source of 2/3 of that. And if we can find ways to produce meat more effectively, explore meat alternatives, we really can make big progress on a huge contributor to climate change. I want to mention one other area of technology solutions before leaving it, not because I think it's a good idea, but just because people ought to be aware of it. And there's been a lot of discussion about offsetting warming by shooting a different pollutant in the atmosphere, one that tends to reflect light rather than to absorb it. And it's often called solar geoengineering or solar radiation management. I'm involved now in work to evaluate whether this would be a cheap and simple way to offset warming. And it looks like the answer is, like most of the technology solutions that we've explored, is the things that look like they're going to be cheap and simple in the early stages are a lot more complicated, a lot more expensive, and a lot more difficult to manage in the long run. And so I encourage people not to be counting on solar radiation management as the ultimate fix, in addition to which it doesn't address many of the impacts of climate change. Okay, let me switch to just a couple of quick comments on finance. I think that the message I want to leave you with in the technology space is that we really have a compelling set of technologies. They're entirely affordable in many cases, but their financial and policy impediments to them being deployed as rapidly as they should. There's sort of two philosophies of the way that decarbonization might spread through the world's developing countries. One is that the developed countries do it first, and these technologies become cheap, then they become the attractive option in the developing world. The other is that we find some way in order to incentivize the adoption of the technologies earlier in the developing world with some kind of cash investments. But nobody's going to invest in any of these technologies unless there's a good prospect of reasonable rate of return. The thing that's been so challenging over the last few years, in the last several years, has been the flip-flopping policy regime where there were incentives and there weren't, and they were back, and it makes it really, really hard to make thoughtful investments. And this expectation of a stable regulatory environment, absolutely fundamental. In addition to that, we already have a whole bunch of subsidies that are in place that favor the legacy technologies, whether it's for electricity production or for liquid fuels, and simply creating a level playing field for the non-emitting options is incredibly important. Another thing that's really important is that the traditional energy sources have access to a whole bunch of important financial tools that renewable energy simply doesn't. And this includes things like long-term loans at appropriate rates or access to master limited partnerships, just a wide range of financial instruments that are extremely important for making something like this work. And then, as I sort of started down the road before, there really needs to be an understanding that it's the companies with the financial wherewithal are either going to do this first and drive the costs down, or they need to start making investments and seeing it happen in other. One of the things I hope was clear in my earlier comments is that climate change is something where even if the US, the entire developed world, finds a way to reach zero emissions in 2050, if that technology hasn't penetrated to the developing world, it doesn't help anybody. Let me say a few things about policy. In the United States, the foundation on which our policies for tackling climate change is based is the 2009 endangerment finding, where the EPA is required to address greenhouse gas emissions. I was involved in a study earlier this year that asked if there's any evidence indicating that the endangerment finding was not robust scientifically. And what we found across every category they looked at is that the evidence is much stronger now, and the range of impacts is much greater than was anticipated. We've been fortunate so far that the one thing that the EPA has not tried to roll back is this endangerment finding, so the legal foundations for tackling climate change are still in place. But it's really interesting when you look at the specific policies, there's a super wide range of things. So, for example, there's an investment tax credit on solar, illustrated in the upper right panel. California has a low carbon fuel standard that's been important for decreasing emissions from light vehicle transportation. And there's been a ton of discussion about implementing a carbon tax. As you know, California has a cap and trade, which is kind of similar to a carbon tax. And economists always argue that putting a price on carbon is the most effective way to decrease emissions. The experience in California, I don't know how many for Californians, but for every 10 environmental regulations that are released in California, 9 of them get tied up in lawsuits. And so I'm a big believer in going with multiple approaches. But there is an expectation that a carbon tax of $50 a ton, that's about 50 cents on a gallon of gasoline, would push us off the current emissions to something that's well within the standards of the Paris Agreement and would reduce emissions by something like 50%. When we think about policy, it's important to recognize it's not just the federal government. I said a little bit about California. There's also really a lot of encouraging progress going on among corporates. Walmart has a project called Project Gigaton. It's intended to remove 1 billion tons of CO2 from their supply chain. We don't often think about Walmart is a leader in environmental efforts, but this is by far the largest corporate commitment to sustainability. And Walmart has an emissions profile. It's about half as many emissions as we have across all of California. So really giant impacts. And they're ones where Walmart is taking partly as a good governance investment, but partly because they see themselves saving money as well. Let me just say a couple things about adaptation. You know, we tend to think about, if we want to solve the climate problem, that what we really need to invest in is decreasing emissions. But I hope the message that you're taking from my comments is that what we really want to do is produce a livable world in the future. And that livable world has got to be a mix of keeping ourselves in this world of ambitious mitigation so that adaptation can work. And adaptation can work. We know that it often produces win-wins in terms of economic development and protecting people from disasters. It's everything from building smart infrastructure, having good insurance mechanisms for sharing risk. Early warning has time and time again proven it to be the most effective investment in protecting lives and property. In some cases, we're seeing that protective structures, things like seawalls, really work. And increasingly, people are looking at not only the need for relocation, but options for using relocation, moving individuals, communities, whole island populations, in a way that it isn't declaring defeat, but moving toward a better life. So, you know, the way I think about adaptation is that we want to be preparing for tomorrow while we're improving our competitiveness and resilience for today. Okay, I want to talk about one other theme that's really important in all of this, and it's really striking how the global conversation about climate change just been galvanized by a 16-year-old Swedish girl. You know what? The attention that Greta Thunberg has brought is really amazing. I could go on for years and never capture the kind of attention that she has, as you guys know. But leadership is really important, and the rest of the world looks really closely at a plot like this. It says, who's responsible for emissions over decades? And you probably know that now China is the world's largest emitter on an annual basis, about almost twice as much as the US. But historically, the big emitters are Europe and North America. And that really is viewed by the rest of the world as a strong indicator of responsibility for being the first actor. But leadership's not just about historic responsibility. It's also about competence and capacity. If you say, well, what's it going to take to solve the climate challenge? It's things like being able to mobilize finance. It's about being able to manage international logistics, to make thoughtful investments in R&D. And those are things that the rich world, and the US especially, are historically good at. And I would argue that they represent an opportunity to take a leadership position. And to capitalize on that leadership position by building the companies and the jobs of the future. A final aspect of this leadership that's incredibly important is that we're seeing a wide range of impacts of climate change on issues that impact national security. The Air Force Base in Mississippi, but we see climate change driving conflicts around the world. And if we want to have a stable world, then an investment in climate leadership is going to be really critical. So how do we get there? Let me just say, I think we can find the Accelerator Pedal. At this point, policy action at the stage of the U.S. government, really central, but there are a whole bunch of investments that can pay off. The most important one is that climate change needs to shift from being the 8th priority on people's need for action to being the first or the second or the third priority. And once it is, we can implement programs that are really comprehensive and systematic. people say, well, don't we need to go to a war footing? And the magnitude of the problem, it actually doesn't require that kind of a commitment. It's a commitment more like a commitment to build the interstate highway system in the 1950s and 60s. If we doubled investment in tackling the climate problem, we could put ourselves on a trajectory to be close to that world of ambitious mitigation. The second thing that we need to do is really up our investments in R&D. This is a picture of the Elon Musk Hyperloop idea that would provide airplane travel speeds on the ground with essentially no emissions. And I have no idea if that would work, but we need to be looking at solutions that are over the horizon now. The third thing we need to do is recognize that not knowing what's going to work, that we need to be pursuing multiple options, and that ranges all the way from things like encouraging the increase in the area of forests, stopping cutting down forests because they're our cheapest, most effective natural carbon sinks, to things like meat alternatives, reducing emissions from agriculture, to making fuels from hydrogen. I don't know which are going to work. We want a portfolio of options that we can invest in. We also need to manage adaptively. We're going to face changing conditions, and we need to be able to deal with those in a way that's not incredibly disruptive, like shutting off the power. This is a picture of the Thames Barrier in London. It was designed to be activated under flood conditions maybe 1 or 2 times a decade, and it's now operated dozens of times a year, and it was designed so that the level of flood protection could be increased with a modest investment going forward. And then the final thing that we really need to do, and it's where I feel like we in the scientific community have done the worst job of making the case, is that we need to capitalize on the opportunities that are inherent in tackling climate change as well as the challenges. And when we really look across the spectrum of building out new technologies for mitigation, new technologies for adaptation, new tools for finance and policy, what we're really talking about is building a robust economy and vibrant communities for the 21st century. We're building a better world, and it's a world that I think we should be aspiring to.